Right, I've just got through all the components and materials which I'm going to use to make my milling attachment for the Myford ML7, and I'd just like to go through what I've actually bought and roughly what I'm going to do, and I'm going to show various machine operations to actually complete the milling spindle. So firstly, I've got some aircraft grade aluminium, which is 6082 T6 grade, and it's 150mm long and 57mm in diameter. Next I have this nice heavy duty aluminium bracket or holder, which is made by Myford, and this is actually used to hold the motors that I've shown in my earlier videos. It's 52mm in diameter and it's solid cast aluminium, and it comes with 4 6mm Allen bolts to secure it to a surface. Next is this C20 ER20 collet chuck on a 150mm long shaft, and it's 20mm in diameter. And lastly, I have two high quality heavy duty tapered roller bearing sets. These measure 47mm in diameter and have a 20mm bore to fit this 20mm ground shaft, and they're a really good fit on that shaft. So this is a really quick and easy method of actually making up spindles or live centers or whatever, because you have these ER collet chucks now with these long ground shafts. The longest I've seen so far is 150mm, which is this one. I think you can get them in 100mm. It's best to actually just go for the 150mm length, because you can always cut them down if you want to. And like I say, I've made live centers out of them and various other tools, and like I say, they're ground very accurately and always fit the bearing that they are meant to. Incidentally, I've just got this micrometer. It's the first digital 0-to-1 micrometer I've owned. It's really high quality, heavy duty. The battery compartment's in the back there, and you have a lock on there for the actual spindle. You have inches and millimeters, which is great because I find myself working in both those these days. On-off button, inches and millimeter, and the increment set it to 0. What I like about this one as well is if you put it into inches and turn it off, when you turn it back on again, it's still in inches. It doesn't actually revert to millimeters, so it leaves the last setting. And like I say, I find that it's really nice to actually have a digital micrometer now, and the quality is absolutely brilliant. Another thing I actually like about this micrometer is the really large display, and the way it's been marked on the barrel as well. It's actually been marked up with the metric increments. The thimble's very positive, and overall I think it's a really brilliant piece of equipment for the money. And it comes in this really nice heavy duty plastic box with the pass details and instructions and the adjustment spanner. And another thing that I really like about this micrometer is the fact that when you actually turn it off, no matter where it is, it will actually always come on with exactly the same reading if you haven't actually moved it. So you don't have to actually re-zero it every time you turn it on. And also, if you turn it off and you actually move the spindle, it is actually still measuring, because when you come to the 0 point, turn it back on again, it's on 0. And I think that's really good. Like I said, I don't know whether it's the same with all digital micrometers, because this is the actual first digital 0-to-1 that I've owned. And I did get the micrometer for the actual quick conversion between metric and imperial, which makes things really quick in the workshop. So this one is just a fraction under 20mm, and it doesn't taper at all, so it's really good. And like I said, when you come to put the bearings on these shafts, I found them to be a very nice tight fit. You have to actually move the bearing about until you get it dead square before it'll actually go on. And when it goes on, you can actually hear that it's a really nice fit. So now I'm going to show various machining operations on the Myford ML7 to make the housing for this spindle and to actually fit this housing to the motor clamp. Right, it's all zeroed up and ready to machine, but with this length of bar it can be quite dangerous to actually face off. There's a danger of actually ripping it out of the jaws if something went wrong. So for those that are new to lathe work, what I do is put it in the jaws like this, zero it up, and then I centre drill it, and then I put a live centre in the end and then face off as far as I can go without actually touching that live centre. And this is the safest method of actually facing off a long bar which won't go up inside the chuck, and there's a lot of overhang. So it's a rough sawn end, but it's reasonably flat. You couldn't do it if it was really at an angle. You'd have to flatten it off on a belt sander or something first to use this method. And then I use this type of live centre with a narrow or small diameter spindle. And then I turn it round in the jaws, zero it up again and face off the other end. When I drill this, it will just drill that little shoulder off, and that will completely disappear, and it's safely faced off at both ends. So now I've drilled it out with the 22mm drill so far, and now I can put in the 14mm drill again and go even deeper. So then I just keep alternating between the two drills, the 22mm and the 14mm. When the 22mm one goes down, it gives enough clearance for the swarf to come out for the actual 14mm one to go much deeper. And like I said, I just keep alternating between the two until I've got over halfway. Then I turn the billet round and do the same from the other end until both holes meet up and it's drilled through. So now I've finished the drilling through, and I'm going to be boring out each end to accept the tapered roller bearing so it's a nice tight push fit. And I'm going to bore it out obviously to the width of the bearing plus an extra 10 thou so that I can actually fit a cover over the end when it's finished to protect the bearing from any swarf or anything. And you'll notice after the drilling up I've completely cleaned the lathe down again. It's much safer and nicer to work with a clean machine. And I haven't got a steady for the bar. I want to get one day, so I'm going to have to very carefully bore it out. And I'm going to be using one of these tools here, this brazed on carbide tool. This comes in a set like this, and I've had a set like this for probably about 8 years now, and they last really well. I'll put the links below where you can actually buy them. When you get them, you have to increase the angle slightly, and I showed it in another video to make them cut really nice. And I'm using a very small boring bar like this for safety reasons, because if anything goes wrong, it's more liable to actually bend the tool off rather than actually knock this out of the chuck. Plus there's more clearance for the swarf to come out. So now I touch the boring bar on the front face, and to get the depth right I can actually put the bearing on the front face of the saddle there and slide the stop up to that and lock it up. So now I know that boring bar will go to the exact width or the depth of that bearing, and then in the end I can let it in by about 10 thou and just skim down the back face. And I'm going to take very light cuts until I get the diameter correct. And it's about 760 RPM. So there's about 14 thou to go, maybe 13 thou. So I'll just take a few very light cuts and spring cuts to get it to size, and I'm using the feed so I get a nice finish. And I've slowed the RPM to 230. That feels just about right to press that bearing in. And the width of the bearing is about 0.600 thou, and I've actually taken that depth to 615, so that's actually ideal for when I fit a cover. It won't actually rub the front of the bearing. And before I take it out, I'm going to rough bore the back face until it's a little bit bigger than the back end of the bearing here. A little bit of a bore to a certain depth, so that I can actually get a tool in there in the future if I actually want to knock the bearing out from the other end. Right, so now I've finished that counter bore at the back, so I can actually make a tool up to push the bearing out if I need to. The diameter of the bearing is 47mm, and I've made that counter bore 43mm, so there's plenty of land on the back of the bearing there if I make up a tool with a leg to actually push the bearing out. I've put an inch diameter drill most of the way through from this end now, and I am opening up the bore a bit with this tool here. And it's an S12M SDUCR07 tool, so it's 12mm diameter shank, and it's a DCMT 070204 insert. Nice sturdy tool to actually open up that through bore a bit. So I've set it so it's just over halfway on the stop, and I'm taking it in and letting it cut with the feed. Right, so I finished the first end and deburred it, and now I've got to turn around and do the other end. So I'll show that in another video, part 2. I need to make a bung up here for this one here so that I can actually put it in the jaws safely to hold it, and then machine this end and do the finished turn to actually fit the motor clamp.